Hello, welcome to this lecture. From this lecture onwards, we will start looking at polar codes. Polar codes, as it turns out, are very recent. They were proposed in around 2008 by Erdal Arikan, but it's become very famous very quickly, and it has very celebrated properties. It's a very nice code. It has a very simple structure, very elegant, and very nice performing, good performance. With a very easy to describe decoder. In many ways, it has some of the properties of low density parity check codes, as in the decoder is soft in soft out sort of decoder. You can build a soft in soft out decoder, and then there is a very simple structure. There's a substructure of parity checks and repetition, which are combined in a very intelligent and smart way to create this, and all credit goes to Erdal Arikan for this definition and constructions of polar codes. So let's get started. Like I mentioned, polar codes were invented by Erdal Arikan 2008. The basic idea is one of what he introduced is this idea of channel polarization. How you can take a noisy channel and through clever techniques create ideal noiseless channels and extremely noisy channels out of a single noisy channel. So this idea of combining multiple instances of the channel cleverly to get either noiseless ones or very noisy ones, more noisy ones than the original channel, is this channel polarization. It's sort of like law of averages. You can't change the average, some sort of energy conservation, if you like. The channel has a certain noise level. You can't change that, but if you do enough repetitions, some of them become noiseless, some of them become very noisy. So this is sort of like capacity. It has a very nice information theoretic structure and a wonderful way in which it can be developed from an information theory point of view. Unfortunately, we won't do such development in these lectures. Our lectures are focused on implementation, so we will talk about them in a very sort of direct way, focusing on how to get them implemented, how to implement the encoder, how to implement a decoder, how to get good performance from them. So that will be our focus. Okay. So a few points to note is that these are the first codes to have explicit proofs of approaching capacity. Okay. So that's a very big selling point. These are included as codes for the control channels in the 5G standard. The data channels have LDPC codes. We saw them earlier. The control channels have polar codes in the 5G standard. One of the big differences between LDPC codes and polar codes is the decoder here is sort of sequential. You decode the first bit and then the second bit in a certain order. You decode the first bit, second bit, third bit, so on. Okay, so that's how you do it. So the decoder is slightly different, and you have to think about it differently. But interestingly, the ingredients are the same. The single parity check decoder that we had, the SISO single parity check decoder, the tan H rule, and the min sum. The min sum will play an important role again, and also the repetition idea. Okay, so these are the two key ideas in this decoder as well, but except that the scheduling of the operations is very different, and it's specific and sequential. Okay, and also the definition is not primarily through a parity check matrix. You could do a parity check matrix as well, but this is not primarily done through a parity check matrix. It's done through a generator matrix, and in fact there's this interesting polar transform which controls how the definition is done. We will study that in detail. Okay, so let's get into it without any further introduction. Okay, so the most basic construct in the polar code is the so-called polar transform, or Arikan transform, you can call it. It's a very, very smart idea. It has roots in information theory, and you can wonderfully describe it in information theoretic terms, but we will use a simple operational definition to describe what it is. Okay, so this is the main polar transform. It's a transform which takes 2 bits to 2 bits. It takes 2 bits to 2 bits. Okay, so this is the polar transform G2. There are also longer versions of it. There's G4, G8. For any power of 2, you have a polar transform. But let's start with the basic starting point, which is taking 2 bits to 2 bits. And the transform is very easy to define. It's defined by this kernel or matrix. You can call it the polarization kernel or the transform kernel. It's just 1 0 1 1. That's it. Okay, you have U1 U2. This is the input to the transform. Okay. The output is U1 U2 multiplied by G2, and this is the output. Okay. Remember, this plus is modulo 2 addition or XOR. You can think of it as binary XOR. Okay. So, if you want, you can make a little table. It's quite easy to write down the table for this. The input is 0 0, the transform is 0 0. If it's 0 1, the transform is 1 1. If it's 1 0, the transform is 1 0, and if it's 1 1, the transform is 0 1. Okay. So, it's an invertible transform. It's quite a simple transform. There's nothing more to talk about it, but you will see the way you can use this to cleverly combine and create transforms for longer strings, and then what properties they have. That's crucial. Okay. So, you will see it works out very nicely. Okay. So, all big stories have a very small starting point. So, this 2 by 2 transform is the starting point for polar codes. Okay. So, there is a binary tree representation for this transform. At this point, it really sounds quite redundant and complicated to draw graphs for this 2 by 2 transform, but it turns out as we compose more and more of these together and get larger transforms, this binary tree picture is very important. It plays an important role in encoding, in decoding, in throughout polar codes. This binary tree representation plays an important role, much like the Tanner graph played a role in the LDPC decoders. This will play an important role for polar codes. Okay. So, what is this representation? You have your inputs at the leaf nodes. These are the leaf nodes of the tree. This is also a leaf node. So, this is the sort of the output node of this simple tree. You have the input bit 1 U1 here, another input bit U2 here, and then the output, which I am calling as this U2. Okay. Just to this 2 denotes that it's a length 2 vector. You will see later on we will have length 2, length 4 vectors, and we will combine them in the same way. So, this notation is sort of important to know. So, if I say U2, it means it's just a length 2 binary vector, and in this case it's just the output. So, you have U1 coming in from here, U2 coming in from here. These two are processed at this node, and out comes U1 plus U2 and U2. Okay. So, this is the transform. Okay. So, there is nothing much to describe here. It's very simple representation for what's going on here. So, instead of thinking of the U1 and U2 as bits multiplying the matrix on the left, we think of U1 and U2 as coming from the leaves of the tree, and they come up the tree and they get processed at the next node, and out comes the output U1 plus U2 U2. Okay. So, remember this again, whenever you go up a tree, you are going to do U1 plus U2 and then U2, retain U2 as it is, and you do U1 plus U2. Okay. So, this is a rule that we will remember. So, this is a combination rule for combining incoming bits. Okay. So, whenever bits come in, what do you do at the node? You take U1 plus U2 and U2. So, this is a simple transform. You will see these are composed together in a clever fashion to get larger transforms. Okay. So, but this is a basic transform. Make sure you have a good hang of it, because as you go further down the slides, this will be used in more and more interesting ways. Okay. So, this is G4. Okay. So, I said G2 is a 2 by 2 transform. G4 is going to be a 4 bits to 4 bits transform. Okay. It takes inputs 4 bits and puts out output 4 bits, and its kernel is done using what's called a Kronecker product. It's also called tensor product of matrices. Sometimes Kronecker product is very popular. How do you do the Kronecker product? If you have Kronecker product of two matrices A and B, what you do is you replace each entry of the first matrix by that entry times the second matrix. Okay. You replace 1 with 1 times the second matrix, okay, which is what you did here, and the second entry 0 gets replaced by 0 times the second matrix, which is what has happened here. Okay. And likewise for the third entry and the fourth entry. Okay. The third entry got replaced by third entry times the second matrix, and the fourth entry got replaced by fourth entry times the second matrix. Okay. So, from a from two 2 by 2 matrices, you end up getting a 4 by 4 matrix, and that becomes the kernel for G4, which is the 4-bit polar transform or the 4-bit Hurricane transform. Okay. So, this is the key idea here. Okay. So, you compose or you product out Kronecker product out two G2s to get G4. Okay. So, now if you multiply with 4-bit input here U1, U2, U3, U4 with G4, this is the output you are going to get. Okay. So, it is easy to see. So, this one U1 plus U2 plus U3 plus U4 is the first one, U2 plus U4 is the second one, U3 plus U4 is the third one, and U4 itself is the fourth one. Okay. Once again, remember, plus is modulo 2 or XOR, right, binary XOR or modulo 2. Okay. So, any input will give you the output, and it is also invertible. You can prove this in multiple ways. It is an invertible transform. Okay. So, this is the 4-bit polar transform. Okay. So, this 4-bit polar transform also has a tree representation. Okay. So, it is sort of built in the same way. You have so you remember, this is like the first G2, this is G2, this is another G2, right. So, you have U3, U4 and U1, U2 going through two G2s. Okay. You get two vectors of length 2. So, this is the output of G2, right. So, the G2 gives you this output, this G2 gives you this output, right. U3 plus U4, U4. Whenever 2 bits come in, right, U1 comes in here, U2 comes in here. What do you do in the combination? Rule for combination is U1 plus U2, U2. Same thing happens here. When these two bits come in, U3 and U4, you simply do U3 plus U4, U4. Okay. And then what do you do for the next level? So, when you go from G2 to G4, you take two such things and then combine them further again. Okay. How do you combine? The same rule. Okay. So, this goes on this edge, this U2 goes on this edge, and what do you do to get U4? This is the output. You combine them again. How do you combine them? Two sets of bits are coming in. Now, these are not single bits anymore, these are 2 bits. Okay. So, these are 2 bits, 2 bits. Remember, this is 1 bit down here in G2, you got 2 bits out. If you have 2 bits coming in, you will get 4 bits out. How will you get the 4 bits? You take these two incoming bits, you add them, keep them as the first part, and the second one alone you retain as the second part. Okay. The same rule that you use over and over again, you will get the output. Is that okay? So, previously we saw that the G2 was a very simple and direct notation here. G4 is a little bit more complicated, but it is the exact same thing as what this multiplication by G4 achieves. Okay. Except that you have a binary tree representation. You have U1, U2, U3, U4 in the leaves. Okay. These are the leaves, leaf. Okay. And then you have 2 levels in the binary tree. So, this is supposed to have depth 2. Okay. So, this has depth 2 here. The previous one had depth 1. Okay. So, this had depth 2. This is the root, people call this the root of the tree. This is supposed to have a depth of 0. Okay. This has a depth of 1. This level is depth 1, and this level leaves are at depth 3. Depth equals 2. I am sorry. These are terminologies we will use for this tree. Okay. We have a root node which is at depth 0, and then below that root node there are 2 children. These are said to be the children of that root node, okay, at depth 1, and below every child there are 2 more children. Okay. So, each node at depth 2, there are 2 nodes at depth 2, and then below that you have 2 more children. Okay. So, we will also number these nodes. This I will call node 0, this I will call node 0, node 1, this I will call node 0, node 1, node 2, node 3. Okay. So, remember how I am numbering the nodes. I am just starting with 0 on the left and going through 0, 1, etc., 0, 1, 2, 3. Okay. So, now node number and depth together uniquely determine the node. Okay. That is important. So, for instance, 0, 0 is the root, 0, 2 is the leaf, etc., leaf on the leftmost side, leaf that has U1, etc. Okay. So, this is something important to know as well. So, this binary tree representation represents the multiplication by the polar transform to get the 4 bits out. The 4 input bits are at the leaves of the tree. Okay, they are combined 2 at a time. They go to the next level, one higher level, and then there again they are combined. There you will get 2 bits at each node. They are combined further to get 4 bits out. Okay, the combination, the rule for the combination is always the same. 2 bits are incoming, you XOR them, keep them as the first part, and then take the second one alone and keep it as the second part. Okay, so that's what you do in every node as you go up the tree. Okay, so if you do that, you get the transform. This is the binary tree representation for G4. Okay, so you can imagine what G8 will be. Okay, so we had G2, then from G2 we went to G4, which was G2 Kronecker product with G2. Then you will go to G8. Okay, so that's the next step. G8 is the Kronecker product 3 times. Okay. Okay, so you will get a 8 by 8 matrix. So G8 will take 8 bits to 8 bits. Okay, so how do you do Kronecker product 3 times? You already did Kronecker product 2 times before, G4, right? So you can also write G8 as G2 1011 Kronecker product with G4. Okay, so you take G4. How would you do 1011 Kronecker product with G4? You replace the first element with G4 itself. Okay, so you'll see this is G4. You have G4 here, and you replace the second element. Okay, maybe I can do some different colors here. You replace the second element with 0 times G4. Okay, and then you replace the third element. Maybe I'll pick a different color. You replace the third element with 1 times G4. Remember, that's how you do the Kronecker product. You replace each element by that element times G4, and the fourth one, maybe we'll pick a blue or green color. That's the fourth one. Okay, so that got replaced by 1 times G4. So when you think of G8, you can think of it as G2 Kronecker product G2 Kronecker product G2. Okay, it's either that. It's also equal to, like I said, Kronecker product 3 times. You do this first, you get G4. So it's the same as G2 Kronecker product G4. And how do you do Kronecker product? You replace each element by G4. That element times G4. So 1 times G4, 0 times G4, 1 times G4, 1 times G4. That gives you G8. Okay. Now this you can repeat. You can do G2 Kronecker product G8, you will get G16, you can get G32, G64, G128, 256, 512, 1024. Up to 1024 is actually used in the 5G standard. Okay. So this is how the G8 looks, and you can take 8 input bits and you will multiply with G8 and you will get the 8 output bits. Okay. And you can also have a binary tree representation. Okay. So here you have the root at depth 0. I will just write D for depth 0, node is 0. You have node 0, node 1, this is at depth 1. Then you have node 0, node 1, node 2, node 3, this is at depth 2. Then you have node 0, node 1, node 2, node 3, node 4, node 5, node 6, node 7, this is at depth 3. Okay. So you have a tree of depth 3, okay, and binary tree, full binary tree, complete binary tree in some sense. Okay, every node has 2 children, okay, all the way up to the depth of 3. At the leaves you put the input, okay, and then you start processing. Anytime you hit a node, the processing is very simple. Okay, if 2 1 bits come in, you get a 2 bit output. Okay, so you have 2 bits here. Likewise, you have 2 bits here. What will these 2 bits be? For instance, if you want to write down these 2 bits, it will be U5 plus U6 and then U6, right? U5 and U6 are coming in, U5 plus U6 and U6. Okay, that's the way you combine. And here again 2 bits, these are coming in, and what will this guy be? This will be actually 4 bits. Okay, how will you combine these two? This will be just U21 plus U22 and then U22, right, for instance. Okay, this one will also be U23 plus U24 and then U24 by itself. That will be these 4 bits, and these 4 bits are combined again to get 8 bits. This is the output, and that's 8 bits, right. So, this is just the exact same thing as multiplication by this matrix, and it has a binary tree representation. Okay. So, this polar transform for any n, okay, it could be G2 or G4 or G8 or G16. You can see how you can do G16, right. You take 2 such things, you have these 2 8 bits coming in, you combine them, you get 16 bits out. Okay. So, you have 16 leaves at the bottom, and it will be a depth 4 tree, and you will have a binary tree representation. Okay. So, this tree representation is very important to visualize to see how the polar code works and the decoder works. So far I have not defined the polar code. Once again, be very clear, this is just the polar transform. This is just a transform from 8 bits to 8 bits. Okay. It takes 8 bits input, puts out 8 bits. Okay. The polar code is constructed using this transform in a very clever way. So, let us see how that is done in the next few slides, but hopefully this transform is clear to you. It is very, very crucial that you have a good idea of what the transform is. You can take a few examples and run through this and see how it works. You can implement this transform in MATLAB. We will do that so that we can do encoding of polar codes. Okay. So, this is something very important to do. All right. Okay. So, what is the general picture? Okay. So, the general picture is you can have a polar transform for n equals 2 power n. Okay. And the small n is 1, 2, 3, so on. Okay. Any number you pick. What is the kernel of this transform? The kernel is G2n. This is the kernel. It has 2 power n bits, 2 power n bits, inputs is 2 power n bits, output is also 2 power n bits, and the kernel is the Kronecker product of 1011 Kronecker product n times. Okay. So, you do it n times. So, how do you actually write it down? So, you can think of it as G2 Kronecker product G2 power n minus 1, which is G2 Kronecker product G2 Kronecker product G2 power n minus 2, and so on. Okay. So, finally, if you want, you can write it as G2 Kronecker product G2 Kronecker product with itself n times. Okay. So, this is the way the kernel is defined. So, this Gn is an n cross n matrix. The binary tree representation will have depth n, 1 root and 2 power n leaves, and the leaves will be at depth n, and this is the multiplication. Okay. So, it is evaluated on the tree with u at the bottom and un at the top, and 5G, like I said, uses up to n equals 10. Okay. So, this is the polar transform, the general picture. Hopefully, this was clear to you, and this is important to understand. Okay. So far I have not discussed what polar codes are. From the next slide onwards, we will start discussing what polar codes actually are.